When a radioactive isotope arrives at a hospital, its measured radioactivity before allowing for background radiation is 4,830 counts per minute. What is meant by background radiation? Now, in the mark scheme, they were very specific about this. And the ideal answer that they gave in the mark scheme for this paper was the radiation still detected when all sources are removed. So when you have particular sources of radiation, when they are all removed, the background radiation is what you then detect whenever all those sources have been removed. It was not sufficient in this exam paper to say the naturally occurring background radiation unless you identified a particular source of that radiation. So they were very, very particular here. If you'd said that background radiation is a radiation naturally occurring due to radon gas or radiation from rocks and soil or inside the body and so on, you would have got the mark. But it's not sufficient to say that background radiation is simply that, naturally occurring. That wasn't sufficient. So I think that is a definition that would be very useful to learn. Background radiation is the radiation still detected when all sources are removed. Now, the next part of the question. The radioactivity of this source, after allowing for background radiation, is measured over a period of several hours. The results are shown in the table below. It plots activity in counts per minute against the time after arrival. The question asks you for a wee bit of your physics skill in terms of graphs. On the grid below, plot a graph of activity on the y-axis. You need to get these the right way round, against time on the x-axis, and draw the appropriate line of fit. Well, first of all, let's sort out the axes. The activity is going to be in the y-axis and the time is in the x-axis. The time goes from 0 to 5 and the activity drops from 4,800 down to 270. So you could say we need a vertical scale to go from approximately 5,000 down to 0 and a horizontal scale to go from 0 to 5. So using a ruler, and in your case a pencil, I'm going to use a pen obviously so that you can see it on the screen, but you must use a pencil in the exam and a ruler. Draw in your axes. Now before I would even start identifying any numbers on the axes, I'm going to label them, because that's the one thing you will forget, is putting the labels on the axes. The y-axis is about activity. When we label an axis like this, we must put the units in. So activity in counts per minute. You could write that as CPM if you wish. And the label on the horizontal, it's time in hours. Now we'll start to put the scale on the axis. We want to go from 0 to 5. 5's at the end, so we'll give 2 squares to each hour. 1, 2. So now we've got our horizontal scale identified. On the vertical we said we wanted to go up to 5,000. So again, I think 2 squares per 1,000 in this one. And the top's 5,000. Now it is quite a small grid in terms of plotting with accuracy, but you just have to work with what you've got. At 0, when it first arrived, it's 4,800. So we get up to the 4,000, that's 4,500, that's going to be 4,800. The most accurate way, I think, to show this in a graph is a dot with a circle around it. At 1 hour, we've 2,690. Which with this scale is going to be difficult to do very accurately, but it's approximately 2,700. So if we come up to the 2,700, put a circle. After 2 hours, it's 1,510. Again, difficult to get it accurate. At 3 hours, 850. Halfway between the 800 and 900. After 4 hours, it's 480, so very close to the 500. And after 5 hours, it's 270, so up close to 300. Now, as you can see, you don't have a straight line plot, you have a curve. It can often be difficult to draw an appropriate line of fit, but what I find is if I turn the page round, I find it a lot easier to do it that way than to try and bring a line this way, but whatever's most comfortable for you. Now, the line of best fit then. Part 3 then asks you use the graph to find as accurately as possible the half-life of this isotope. Oh, just to go back to the graph, the marks that were identified there, you got a mark for labelling both axes, including the units, a mark for having appropriate scales in both axes, you get 2 marks for plotting the 6 points correctly, and the final mark was for having a smooth curve through the points. So the 5 marks again, 1 for both labels, 2 for having both scales accurate, 2 marks then, so it was 1 mark for having both scales accurate, 2 marks then for plotting the points accurately, and the final mark for the line of fit. Now it says use the graph to find as accurately as possible the half-life of this isotope. Let's remind ourselves what half-life is. The half-life is the time it takes for the activity to drop to half its original value. So the easiest one probably to use, I think, is going from 4,000 to 2,000. You could of course go from 4,800, which is your original, to 2,400 and read it off. Perhaps that might be easier. Let's read across at 2,400. So we'll label this as 2,400. And bring your marker down. Again, using a ruler here and a pencil. Draw in your construction lines in the graph. The reason I say to draw in your construction lines is it says use the graph. So you need to identify the fact that you're actually using the graph. And there was 1 mark allocated for drawing these construction lines and the second mark for reading off the value, and the value is 1.2 hours. So 1.1, 1.2 hours. So there was a mark for the lines and a mark for the correct value.